So, next step is talking about the moon. Two things I would like to talk about is how the moon was formed. We see that at the end. And the tides effect. So I told you already that the moon is always showing us the same face. So there is a very good explanation for that. And you know that there are tides effect. If you go to the sea border, you will see the sea rising and going lower. And it's directly linked to the presence of the moon. And I will talk briefly about eclipse. It's a phenomenon that you're probably aware. There will be a partial solar eclipse this June, I think, visible from here. The last one was 2009 or 2008, visible in mainland China. So the moon. So this is a picture of the moon and Earth system. Earth is here and moon is there. And you all know that we have been on the moon, so you can see Earthrise from the moon, for instance. Very nice picture taken by one of the Apollo team. So, if you compare those two bodies, the ratio between Earth and moon radius is 1/4. That means Earth diameter is 4 times bigger than the moon's diameter. And the ratio in mass is around 1/80. Okay, so the Earth is 80 times more massive than the moon. And if you're a bit aware of very simple mathematics, you will see that the increase of radius can't completely explain the difference of mass. It means that the density in the moon is actually lighter than the density of Earth. I'll come back on that. So, this is the moon as you see it all the time when it's full, and it's always showing the same face. So you have several features that you're probably familiar with. There are those dark patches that we call mare, for sea in Latin, and there are those white patches we call continents. Also, you can see that there are lots of craters coming from meteorite impacts. We already mentioned that. And some of them are very, very big. And with this very noticeable ray effect. You can see that. You have a zoom on it. So you see there are a lot of craters. This one is massive, but you have many, many others. And you see that you have those rays coming from it. And those rays are probably coming due to ejection during the impact of it. Okay, so this is another picture from Apollo. So this part, which is darker, seen from Earth, is called Mare Imbrium, and this very big crater here is called Copernicus. So, there are several features that are noticeable on the moon. They were first really discovered by Galileo, the first time he observed the moon with a telescope. And now we start to have a very good idea of what's happening there. So first there are craters. And as you remember from what I told about Earth, they may have two different origins from those craters. Could be volcanic or impact by meteorites. And actually in the case of the moon, it's almost only coming from impact of meteorites. But we have evidences of some volcanic activity in the past as well. There are mountains on the moon. So some of them are due once again by impact, the rise of change of shape due to the impact. But some of them are really band of mountains. There are evidences of plate tectonics in the past, like it happened on Earth. So we have those oceans that we call maya or sea, which are darker. And you have rilles, something like our canyons. So we think that they are collapsed lava tubes. So what's happening on Earth, we see that, is that if you have lava, very hot lava going through the crust, but not going on the surface, but through the crust, it's creating a tube, and sometimes it's collapsing, and it's creating a very deep canyon. Those rays that I showed you, they are radiates from several prominent craters. They're probably due to the ejection of material due to impact, or also can come from lava flows if it's a volcano. So first we'll mention those large-scale features. So the Maya, So you have marinium, tranquillitatis, mer de la tranquillité in French, imbrium. So those dark areas here resemble oceans, and actually we know now that they are plains of solidified lava. So they're actually part of the lunar mantle, and we can date them, first because we have collected samples directly there. So they are around 3.2 to 3.9 billion years. And then we have those highlands or terrae or continents. They are lighted color, and they resemble continents, and they are made out of lunar crust mainly. And they're actually 4 million years old. So what tells us about those two things? Well, these parts that are lighter, those terrae, we know that they're older. We can see that they're older actually because they are far more heated by impacts. So that means that they are exposed since longer than that. While those dark patches, they are younger. We know that by collecting samples, but we can see that they are younger because they have less of these impacts. And they are definitely different colors or different material. What happened is that these dark patches are lava, covered by lava recently due to volcanic activity. And we don't think it's really due to tectonic effect, but also there may have been a tectonic phenomena on the surface of Earth surface of the Moon a long time ago, but it's mainly due by very intense volcanic activity. So when Moon was younger, something like several billion years ago, the number of impact was far higher. We mentioned that already, and we'll come back when we talk about scenario formation of the solar system. So volcanic activity was far more important on the Moon. So there were massive volcanic activity that was spreading lava, so refacing the face of the Moon, and these are the origin of those mare, those dark patches. While in some other places you had no volcanic activity, so what's there is older, it has not been recovered by the fresh lava. It's exactly repainting an old wall. If you have a very old wall, lots of stains and holes and things like that, and from time to time you put a patch of fresh paint on it, it looks newer just on the parts, but it looks older somewhere else. It's exactly what happens here. So volcanic activity has changed the shape in some parts of the Moon, but not entirely. And for some reasons, it stopped. So there's no recent volcanic activity in the past 3 billion years. So since the last 3 billion years, the Moon is totally dead in terms of geologic activity. So of course, you all know, and this is true, don't believe the internet, crazy people saying that it never happened. We've been on the Moon, we have lots of evidences of it. So this is a picture of a Buzz Aldrin taken by Neil Armstrong. So there are 6 landings by American teams between 1969 and 1972. This is the footprint of Neil Armstrong, so the first step of man on the Moon. Moon is by far the furthest distance we ever traveled. And it's funny to see that with the technology that we have in the 60s, we managed to do that. It's a very, very big achievement. And it's sad but true, currently, we don't even have anymore, because they stopped the space shuttle missions. So we don't have anymore any capability to send anyone on the Moon anymore. So we don't think it will happen before a while. Also, Chinese are talking about a space program. And some people are evoking going to Mars, but it's still a very, very long plan. And so at the day of today, we don't think that we'll send anyone on the Moon or Mars before at least 50 years. So of course, none of us were born for this event, but my father told me that when he was a kid, he remembered very well this first step. It was broadcasting all around the world. And my father used to have a TV in his family house at this time, which was pretty rare in the late 60s. So he had the whole neighborhood gather in their living room to see this. And there's a very famous sentence by Neil Armstrong when he jumped from the Apollo on the moon. He said this is one small step for man and one giant leap for mankind. So actually, if you remember, it's more something like, but yeah, that's more or less what he said. It's exactly like when you're going to wherever you're going on Earth, any airport in the world, you never understood what they're saying in their microphone. It's always so the moon is a pretty nice landscape. Actually, they have lots of pictures. So it looks like they had great fun when they were up there. They had small cars. They will jump very high, but there's nothing. So no populations there, no plants, nothing. Okay, it's totally desolated. So many pictures taken by the successive Apollo teams. Actually, one of the research assignment for the homework of the next homework is to look through the different Apollo missions. It's quite a nice story. Okay, so the moon. This is the full moon. So this is the phase you see when the moon is full. You all know that actually this is changing with time. There are phases of the moon from the new moon when you don't see it at all, even so you can distinguish it's there, but it's all dark, and you have quarters, crescents, etc. So those phases are corresponding to how much of the moon is lighted by the sun, is illuminated, and it changes in about a month period. So the phase, that's what we call the phase, is the feature of the surface of the moon, doesn't change at all. I mentioned that already. You always see the same feature. You see this patch here, it's always there. You always see the same feature. It doesn't change with time. So we know that the moon's orbits on Earth every 29.5 days. We mentioned that on the first lecture. And the orbit of the moon, the orbit around the Earth, is slightly tilted. So what that means is this is the sun, this is the Earth. So this is the Earth turning around the sun, and actually the plane of rotation of the moon is not aligned with the plane of rotation of the Earth around the sun. There's a slight tilt, and you will see later it has its importance. And of course, half of the moon is always illuminated by the sun, but it depends which half it is. So that's creating this phenomena of phases. So sometimes only part of the lit up is visible. And what we call the dark side of the moon, there is a very famous album from the Pink Floyd in the 80s called Dark Side of the Moon, something that you hear very often. Actually, it's misunderstood. The dark side of the moon is not always dark. What we call the dark side of the moon is the side we don't see, but sometimes it's lighting up. Okay? So don't get confused with this notion. Okay, so it's pretty simple. You all hopefully have understood that already. This is why we have phases. So this is the Earth, this is the moon turning around the Earth, and this is the sun is over there. So you have lights coming from the sun. So what's happening is when the moon is between us and the sun, the phase that is lit is away from us, so we see it dark. That's what we call the new moon. When the angle of the moon and the sun and Earth is 90 degrees, you see only half of the moon lighted up. It's what we call the first quarter. So between this phase and that phase, you have a waxing crescent moon. That means the crescent increasing with time. Then this part is still getting increased, and when the moon is the opposite direction than the Earth, so it's fully lighted. Okay, so this is a full moon. And once again, it's going back again. Something that you probably understood a very long time ago. And we have another phenomena, it's called lunar eclipse. So sometimes you look at the moon, and the moon is not dark, it's actually red. And this phenomenon, red moons, happen always when the moon is full. So this is an eclipse. What's happening is the moon is entering the shadow of projection of the Earth. So this is where the sun is, this is where the Earth is, And if there is a projection of the shadow of the Earth, this is a dark cone here, and the moon is entering it. So first it's lighted by the sun, then it's entering this light cone, it's getting reddish, and then it's getting out of the light cone. So what you have, several phenomena. So actually, when you see the light coming from the sun to the Earth, there are two shadows. There is a lighter shadow, which is creating by this crossing here, and there is a darker shadow, which is creating by the direct shadow of the Earth. So what's happening is when the moon is entering here, it's what we call the penumbra. It's a bit darker. So you will see the moon is less bright. And then when it's entering this darker part, okay, the umbra, what we call the umbra, then the moon starts to be very dark. And when it's perfectly aligned, it's red. Okay? So this is a phenomenon of eclipse. So another way of representing it, you have the moon motion during the total eclipse, the moon eclipse. So first it's in penumbra, so it's a bit less bright. Then it enters the umbra, and when it's perfectly aligned, it should be almost dark. So why is it red? Do you have any idea? Why it's not black? This is related to something we discussed last week about the color of the sky. What's happening is that the light is going through the atmosphere of the Earth. So you have the sun, the Earth, and the moon. And the light, the main part of the light, there is some light coming from the atmosphere of the Earth, because the Earth is surrounded by this thin layer of atmosphere. And remember that when light is going through a lot of atmosphere, it gets very red. The blue is scattered, but the red light is coming. So the shadow of the Earth is not totally opaque, right? And actually it's projecting a lot of red light due to the glowing of the atmosphere, due to the fact that the light is going through the atmosphere, and only the red light is going through the atmosphere. So that's why the moon is red. So it's exactly the same phenomena why the sunset is red. Right. So now, the next question is, why it doesn't happen every time? Why don't we have moon eclipse every single full moon? Because if you remember this,
degree.
Exactly. So if you remember, when you have the full moon here, the full moon is when you have this configuration with the moon is the opposite side of the sun, and it's fully lit. But the eclipse is happening exactly at the same time, and like you mentioned, is due to the fact that the rotation of the moon is tilted compared to the rotation of the Earth around the sun. So in some cases, in the main part of the cases actually, what will happen is you will have the sun, light coming here, and the moon will be slightly above actually the ecliptic plane. So when it's slightly above the ecliptic plane, then you have a full moon. But as it's tilted, in some cases, here, for instance, you will have the moon that will be exactly in the same plane. Some periodic effect. All right? So that's what this is representing it. It's sometimes due to the angle of rotation of the angle of the plan of rotation of the moon around the Earth and the ecliptic plane. Sometimes the moon will be above, and sometimes the moon will be exactly in the plane. And then sometimes the moon will be under, and sometimes once again it will be exactly in the ecliptic plane. So we have periodicity. So we can predict the moon eclipse. Okay? So this is another way to show it. This is the ecliptic plane. So this is the projection of the shadow projection of the Earth on the sky. And this is the moon orbit. It's slightly tilted. So sometimes when you have a node, you will have a full eclipse, and sometimes you just have a slight effect of eclipse here, when you have just part of the moon that is not covered. And the moon eclipse. So this is a very nice composite picture that you can find once again on Astronomy Picture of the Day. So remember, I told you several times, you go on the website that I gave at the first lecture, and you'd go on that date and you will have that picture. You can have access to it and use it by yourself if you want. So this is what's happening during a total lunar eclipse. So once again, in that configuration, what we have is this. Means that the moon is orbiting around the Earth, okay? And the configuration is that the sun is here, so the face of the is daylight here and night there, and you have the projection of the shadow, and the moon is moving and entering this shadow. So it's full moon time. That means that the configuration is when the moon is lighted up by the sun, that direction. But this time the moon is exactly in the same plane than the ecliptic plane. So the moon will enter this umbra. So the moon is starting to enter the umbra and it's getting out of it. So what you observe is that you start to have the full moon and a little bit that is eaten in there, and throughout the night you will see the shadow gaining over the moon until the moon is very, very small, and suddenly when the moon is totally in the shadow, then it starts lighting up in red. And this red light is coming from the light coming from our atmosphere. So because of the presence of the atmosphere, it's doing exactly like a loop, or when you're zooming, when your glasses or etc., it's deviating the light and converging towards the moon. So you have the Earth, the light coming from the sun, the moon is there, and part of the light is deviated by the presence of the atmosphere. But because the atmosphere is absorbing blue light, there's only the red going through. So at the end, when the moon is totally in the shadow, you see it red because there is part of the light coming through the atmosphere of Earth. So then you start to see the crescent increasing again. That means that the moon is going away from the shadow projected shadow of the Earth, and then you go back to your full moon. So this is when it's exactly in the plane. Sometimes not exactly in the plane, it's slightly above it. So this is another composite image when you have the moon here entering the shadow, but this time the alignment is not perfect, so you only have parts. This is the shadow of Earth, here you can see. So the moon starts to be there, then there, then there, then there, and it's moving that direction, or the other way around, it doesn't matter. And what you see here is that part of it is eaten by the shadow of the Earth, and this time the moon is slightly above the ecliptic plane, so it's not totally obscured by the shadow of the Earth. So here, this black thing is the projection shadow of the Earth. All right? So this happens quite often. So every time you see a red moon, it's an eclipse actually. So there are the other type of eclipse that are far more impressive. It's solar eclipse. They're a bit more rare. So it's exactly the same phenomena but reversed. This time is when the moon is directly between the Earth and the sun. So you have the same phenomena of penumbra and umbra. Okay, so this is the Earth. It's not to scale. Distances are not respected here. But this is the Earth, this is the sun, this is where the moon is. So you have the projection of the sunlight, and the moon is creating a shadow on Earth. So it's very located. So usually the moon, in that case, the moon will be a new moon, obviously. It's the configuration. And the umbra is where the sun is completely blocked. So usually it's about 300 kilometers of diameter. And the penumbra, this part, is when the sun is partially blocked, and it's around 7,000 kilometers on Earth. So here, when you're there, you will see a partial eclipse. Only part of the sun will be eclipsed. And here, you will have a total eclipse. So you also are aware that we have two kinds of eclipse. You have the total eclipse and you have the ring eclipse. So what happened is that you remember the distance between the Earth and the sun is changing with time. So sometimes the moon is exactly the same projected size on the sky than the sun, and sometimes the moon is slightly smaller. So when the the configuration is such that the projection of the moon is exactly the same angular size than the Earth, you have a total eclipse. But sometimes, because you see the difference? Because the moon is the distance is a bit different. So the moon, the projected angular projection, the projecting angle of the moon on the sky is slightly smaller than the one of the sun. You have a ring eclipse. Okay? So if you're in umbra, in that case, you don't see the sun at all. But in that case, if you're in umbra, you see an eclipse. Okay? Sure?
The distance between the Earth and the Moon is the same. Is it just between the Moon and the Sun? Or
It's both, actually.
is it both?
The orbit of Earth around the Sun is slightly ellipsoidal, and the orbit of the Moon around the Earth is slightly ellipsoidal as well. So it's a combination of both. So it's almost actually, well, we can debate on that as well. But we know also, I don't know if I mentioned that during that lecture, but we know also that the Moon is moving away from us. So we have a recession of the Moon. The Moon the projection of the Moon will get smaller and smaller and smaller. But what it tells us is that at the age of the dinosaurs, you probably didn't have any ring eclipse at all. And in the future, we'll have more and more ring eclipse. Okay, it's not talking about the future of us, I'm talking for our grandchildren. But, so this is the angular size of the Moon when it's the closest to us, at the perigee, and when it's more away from us, it's the apogee. So it's changing, and we have the same thing with the Sun. So it's both of them, a combination of both. So when the Earth is near perihelion and the Moon is near apogee, we see an angular solar eclipse. So when you have the two extreme cases, this and this one, you see it. Okay, so what are eclipses? Are there coincidences? How come that the Moon can eclipse the Earth? So what happens if the Moon is closer, say twice as close? And what happens if the Moon is further? And what happens if the Moon was twice bigger or the Moon was twice smaller? So this is really a coincidence that a day of today, the angular size of the Moon and the Sun are exactly the same. Once again, it not have been the case in the past and won't be the case in the future. It's just a coincidence. Or not. So everything is about angular size. So I mentioned that several times, and this is something that is coming very often in astronomy. So what we call angular size or angular diameter, we measure everything in projecting angles. So this is a woman looking at the Moon. So this is the linear diameter of the Moon. But actually, if you look on the sky, you can measure it as an angle. And this is related to the distance. So this angle alpha in radian can be measured exactly like twice the arctangent of the ratio between the size of the Moon and twice the distance. And if the alpha is very small, you can have a linear correlation. That means alpha equals L over D. So the real size divided by the diameter. So remember, P radian corresponds to 180 degrees. So alpha in degrees is alpha in radians, 180 divided by pi. So if we measure this angle for the Moon in terms of degrees, this is the average, the size of the Moon, 3,476 kilometers. This is the average distance, 380,000 kilometers. So you do the ratio, you get around 0.5 degree. Now you take the Sun. This is the size of the Sun, the diameter of the size of the Sun. This is its distance, and you do the ratio, it's 0.5 degree. So it's a coincidence, but currently, on the day of today, the Sun and the Moon have exactly the same angular size. Right. So like the Earth orbits around the Sun, the orbit of the Moon around the Earth is not a perfect circle. I mentioned that already. So there is an eccentricity of the Earth orbit around 0.016, and the eccentricity of the lunar orbit is 0.05. So the distances between those three bodies changing with time. So that's what I mentioned before. This is why we'll have different type of eclipse. So now, we understand very well the cycles. It's not extremely complicated. So we should be able to predict exactly where and when eclipses happen. So there is first the combination of the motion of the Moon. So remember, the Moon orbits the Earth with a period of 29.5 days. Remember that there is a tilt of the orbit of the Moon with respect to the ecliptic, which is at the origin why sometimes we don't have eclipse, sometimes we have some. There is also a precession, so the precession of the lunar orbit with the eclipse. Sometimes the moon is in the ecliptic and sometimes it's not there. So if you do your math, you can see that an eclipse occurs with a period of around 18 years and 11 1/3 days. This is what we call the solar cycle. So every 18 years you will have an eclipse, solar eclipse, you know that. But those eclipses don't happen exactly in the same location. Remember, the size of a full eclipse is only 300 kilometers and can be anywhere on Earth, depending on the configuration. So it's actually happen in a given location far longer than the solar cycle. So this is actually a nicer representation of the effect of the ecliptic. So this is, imagine that the ecliptic is just like the surface of water. So you have the sun here, the earth here. The earth is turning around the sun on this surface of water. But the moon is slightly tilted. The axis of rotation of the moon is slightly tilted compared to the ecliptic. So sometimes the moon is below the water line, and sometimes the moon is above the water line. Okay? So when the moon, the earth, and the sun are exactly on the water, then you have a total eclipse happening. That's an idea. So this configuration here is unfavorable for eclipse. You have the moon below. Same thing here. But in that case, it's favorable for eclipse. So you can compute that. So we can forecast exactly where and when and for how long those eclipses happen for hundreds of years. So this is all the solar eclipse that will happen between total eclipse that will open 2004 and 2030. So like I told you, in July 2009, it's probably I'm not sure if it happened I was not in Taiwan yet. I'm not sure it happened, but I know that it happened in mainland China. Definitely from Taiwan, you saw in summer 2009, you saw the partial. There is a partial eclipse that will go actually this year due to, I thought it was June, maybe it's November. It will be partially seen from Taiwan as well. So you see all those different, so the next one, if you really want to see the next one, you have to go in New Zealand in November, then you will have a full eclipse. And after that, you will have in November, etc. 2013. So there are people that are actually chasing eclipse. I know a couple of astronomers, a friend of mine, they are going to witness any solar eclipse.
Does the picture mean the full eclipse?
It's where it's the track of the full eclipse.
Full.
Yeah. Okay, so it's actually I witnessed one myself in the. Was this? No. Was it 1999? Correct? Yes, 1999 in France. We had it's not on that piece from 2004. In 1999 in France, I witnessed one. So I don't know if any of you has been witnessing a total solar eclipse once. It's a very impressive thing. It's very impressive. First, the temperature drops dramatically. You lose 5 degrees in a fraction of a second. That's weird. And then suddenly everything is quiet. All the birds going to bed. I was in a field that they were surrounded by cows. Half of the cows were starting to try to sleep. The other half, so they were very confused. It was very funny. That's something that people that have seen total solar eclipse will always tell you. Just before it was entirely covered, and then suddenly the clouds disappear and you see the eclipse. This is obviously directly linked with the change of temperature. So the temperature is dropping very rapidly, so actually the cloud coverage is diminishing very rapidly. So if you have the opportunity to do it, it's a very nice thing to witness. It's not very long, but it's a very, very nice atmosphere. If you do it, please remember to protect your eyes. Because, of course, don't stare at the sun. So this is another montage with a different snapshot of an eclipse that happened. So when we talk about the sun, probably in a few weeks from now, I will talk about this corona effect. So this is during the total eclipse. You can see actually the fact that the sun is not very quiet. And you can see this corona. That means there is lots of light around the sun. It's quite impressive. And this is the eclipse I've seen from space. So this is the shadow of the moon on the Earth. So it's around 300 kilometers, and you see that there is a penumbra around 7,000 kilometers around there where you have a bit less light. So sometimes you have very nice pictures. So this is a partial ring. Okay? Do you have any questions about the eclipse?
Then the partial eclipse will happen more than full eclipse.
So the day of today, I can't remember the ratio, but it's more rare to have a ring eclipse than a total eclipse currently, because you need to very particular configuration, because the angular size of the moon and the sun are very, very similar. So there are slight changes. But as I mentioned, the moon is moving away from us. So in 1 million years, probably we will have more often ring eclipse, because the angular size of the moon, because moving away, will be smaller. Okay, so mentioned that several times as well. The moon is always showing us the same face. Okay, so if you look at the face of the moon, indicating here, you will see that it always looks the same. Whatever you're doing, when you look at the moon, it's always looking like that. Always. Actually, the moon looks differently on the other side. We have pictures, but if you want to see that, you need to take a spacecraft, because you need to be the other side of the moon. So there is what we call the lock-up effect. The fact that this moon, the moon is always showing. So imagine that if I'm turning around you, but I'm always watching you. Okay, that's exactly what the moon is doing. So there is a synchronization between the rotation of the moon around the Earth and the rotation of the moon on its own axis. And actually, it's coming from tidal effects. Tides and tidal effect are mechanical effects due to gravity, and they are extremely important in the solar system. And I will come back to tidal effect a lot when we're talking about the solar system. It's a very important phenomena, physical phenomena. So today I will try to describe briefly, but I'll come back over and over again, because you see it everywhere. So tides, you're pretty used to this tides effect. So this is a picture I took myself from where I'm from. I was raised near the sea border in France. So you all know, and it's very noticeable where I'm from, because sometimes it can be 10 kilometers away. Every 6 hours, the water is rising and going down. And there is a cycle. So sometimes you have up tides, and sometimes you have low tides. And if you are fanatic of shellfish, when you have low tides, you can go and pickle mussels and clams and shrimps. It's pretty good. So, what is the origin of the tides? This is due to the presence of the moon. So actually what happens is that, so once again, this is not really to scale, but this is the atmosphere, or you can imagine this is the sea, for instance, the water level. And what happens is when the moon is, when the water is attracted by the presence of the moon, so it's deforming the shape of the atmosphere and the shape of the water, because the attraction of the gravity by the moon is stronger here. So the way you can show that is through gravity. So imagine that you're here, I'm here, and I have one of my hand that is attached by a string, another part of my hand that is attached by a string. And both are pulling the same direction, but here I have two of you pulling, and here I have four of you pulling. But you're both in the same direction, both of the same direction. But in that arm, I have more people pulling, and in that arm, less people pulling. What will be the effect is I will rotate. Okay? I will be pulled more, stronger than there. I will be rotated, and I will enter to that configuration where I have one arm tilted and the other one tilted the other way around. Okay? So what happened here is I have a stronger force here and a weaker force here. So what I will feel if I can't rotate, is what we call a differential effect. And it would exactly be like, there's only white, doesn't matter. It would be exactly be like, I have, so 3 people putting here, and 3 people putting there. No, sorry, 1 people putting here, 1 people putting there. This is exactly the same thing for me in the center. Okay? I have 2 people putting, I have 2 strings going that direction, but one is stronger than the other. That's exactly on my body the same effect that if I have 1 people on each side putting me. Okay? So the same thing with Earth. What's happening here is that because the moon is closer, the attraction here of gravity is stronger than the attraction on the other side. So as a net effect on Earth, it's exactly that it's pulled that direction, stronger. Okay? Moon is attracting both sides of the Earth, but due to the distances with different forces. And here it's stronger, and here it's less strong. So as a result for Earth, that has a net effect to that direction. So this is creating a tidal bulge. That means that this part of water on that side is attracted stronger by the moon. So it's deforming the shape of the atmosphere and the shape of the water ocean. Actually, the shape of the Earth as a global, like a potato. Okay? So, actually it's a bit more complex than that because this is not totally synchronized. So what happened is while the moon is turning around the Earth, this is the Earth's rotation, this tidal bulge, this deformation by the presence of the moon is turning as well. Okay? Because the Earth is turning on its rotation, so this thing is turning as well. So there is the moon going there, creating this deformation, but all those things are in motion. So as a result of that, there is a feedback of the tidal effect. That means imagine that the moon is not moving, but the Earth is turning. So this bulge that is there, due to the rotation of Earth, is slightly tilted. So sometimes the bulge, the peak of the bulge would be there. Not directly aligned with the moon, but to be there because of the rotation of the Earth. So this has an effect on the moon, feedback effect on the moon. It means that here, there is more mass than here. So the moon will be attracted to that direction. Okay? So there is a feedback effect. The moon, the presence of mass of Earth is higher here than here, so it has tendency to change the rotation of the moon. So if you combine those 2 effects, there is the bulge, okay, and the bulge is rotating because of the moon, and this rotation of the bulge due to the rotation of the the bulge is rotating because of the rotation of the Earth. So the rotation of the Earth is moving this bulge and has tendency to attract the moon further. So the moon will change slightly its rotation as well. So if you do that many times, what's happening is that after a while, you have the moon that is totally locked up to always look toward that bulge. So the rotation of the moon on its axis, when the bulge is up, is slowed down. Imagine the moon is turning this way, this direction. Okay? So what's happening, for instance, if it's turned this direction, then when the bulge is up, it has tendency to accelerate. And then and the other way around, if the bulge is in that direction, it will have tendency to decelerate the rotation of the moon on its axis. I think the next slide is showing exactly that. So there is balance of those 2 forces, and this stuck the moon to always face the same, to present always the same face toward the Earth. The combination of the rotation of the Earth and the bulge, the tidal effect, is stucking the moon on it, showing always the same face to the Earth. There is a synchronization effect. Is that clear? I know it's a complex, so there are 2 phenomena here. First, the tidal, the fact that the moon is attracting part of the Earth, so it's deforming the Earth. You have a bulge. But this bulge is also rotating because the Earth is rotating on its axis. And this displacement of where the bulge is has an effect directly on the rotation of the moon as well. And if you combine them together, what happens is that the moon is totally, due to the tidal effect, the rotation of the moon on its axis and the moon around the Earth is totally synchronized, and you always have the moon showing the same face. So this is the summary of what I've just said. So this tidal effect here, so you have the moon, so you have the gravity is stronger to that side because the moon is closer than to that side, and this is exactly for the moon, exactly like having things pulled other side. The differential effect between this scheme and that scheme is exactly the same. Having something stronger on one arm than the other is exactly like having things pulling you away both sides. So this is why you have this deformation of the bulge. Both sides, okay? So the moon is only one side, but you have deformation in both sides for the Earth. Okay? Because of differential effect. And then there's excess of centrifugal force, the fact that the Earth is rotating on it, will have tendency to pull the moon towards us. So we have something that we call the spring and neap tides. If you're quite familiar with those phenomena, they are in spring, the tides are far stronger actually than the rest of the year. So what happened here is, imagine that you have the sun, the moon, and the Earth. So the moon for you and the full moon. Okay. So then this configuration of alignment, the sun and the moon are working together. So the gravity here is stronger because you have the sun here, the moon there, everything is aligned. So the effect on the tides is stronger because of the sun. Sun, moon are aligned with us, so they are contributing together to increase the strength of the tides. But on the opposite, when you have the sun here and the moon there and there, okay, so then they are cancelled out somehow. So the tide will be less strong. So we have a combination of gravity of the sun and the moon that is creating stronger tides in spring. And once again, due to the fact that this deformation of the bulge of the moon is rotating at the same time that the Earth is rotating on its axis, then you have what we call tidal friction or feedback effect on the rotation of the moon. So the Earth's rotation drags the tidal bulge with it, and there are friction that occurs because actually there is a delay because the water is not moving perfectly, so there are delay. So this tidal effect has many effects on Earth and the moon. First, due to this tidal effect, you have the Earth's rotation is slowing down by something a fraction of a second every century. Due to the fact that this bulge is difficult to drag, you have this heavy weight to pull away, it's slowing down the rotation of Earth on its own axis. It's also have an effect on making the moon spinning away from Earth. It's like every time the bulge is coming here, it's just like kicking the moon away. It's more or less the same thing. So you have a bulge coming in, bang, it's kicking the moon away. So because you have more mass here, and imagine that it's going, this amount of mass is turning, every time it's going closer to the moon, it has tendency to spin it away from us. So this creates also the fact that the moon is moving away from us, I told you. So before the moon was closer, but due to this tidal effect, every time this bulge, peak of the bulge is closer to the moon, it has tendency to push it away. So for physicists, it's a very good example of conservation of angular momentum. So in terms of physics, mechanics and physics, it's a very nice exercise to do. You can compute all that actually quite easily with very simple mechanics. Of course, all those phenomena, all those effects are extremely small, but we're talking about things that happen on the scales of billion years, once again. So this slowdown of the rotation of the Earth is a fraction of a second every century, but imagine the Earth is 4.5 billion years. Imagine that it has had a strong effect since the start of the Earth. So the rotation of the Earth is slowed down because of the presence of the moon. Same thing with the spinning away of the moon. 4 centimeters every century compared to 384,000 kilometers, that's nothing. But you put that on billion years, and then it starts to be very important. So the tides are very convenient for us to go to pick up shellfish, but also have a very strong impact on the couple, moon and Earth. And it's one of the main reasons why actually the moon is locked up and always looking at us. So I understand it's a difficult concept. We'll come back over and over again once again when we talk about satellites and when we talk about the other planets in our solar system. This is a very, very important effect. So think about it, and please ask me questions, because I'm sure that it will take time to understand all of it. Okay, so now I will finish for the last 15 minutes about the last topic, is the formation of the moon. So I didn't have time to mention too much about it, and I will spend the last 15 minutes talking about that. But our moon is a very peculiar object. And when we start to look at the other moons, the other satellites around the other planets, we'll see that actually our moon is very weird. First, too big. If you look at Mars, it has 2 satellites, 2 moons, they are very small. Venus doesn't have any satellite. The giant planets, Jupiter, Saturn, Uranus, they have many satellites, but the ratio between their mass of the planet and the mass of the satellite is very small. So the satellites of the giant planets are very small compared to the total mass of the planet. But our moon is only 1/80 and 1/80th, 1/80 of the mass of the Earth, which is very weird. Secondly, something I won't have time to mention today, but we mention again, the moon is our good guardian. Because it's so big, it's acting like a shield. So for the early phases of the existence of Earth, there was lots of asteroids and lots of comets and lots of rocks around us. And actually the moon was acting like a shield and was protecting us from impact, and probably will act again. So when you see those movies like Armageddon or Deep Impact that were very popular a couple of years ago, they always forget to mention the fact that the moon is there. And the moon will probably protect us if any major impact will happen. So, the question is, if our moon is so peculiar, how did it form? We think, we come back on that when we talk about Mars, we think that the satellite of Mars, the 2 moons of Mars, were actually captured by Mars. So there are a rock coming too close to it, and no, this is mine. And it's just turning around Mars. But the moon is very peculiar, so was it captured? How? When? And what happened since the formation of the moon? So we have several scenarios to explain the origin of the moon. Like I mentioned, the large size of the moon poses lots of problems for planetary scenario formation. So some ideas are, well, maybe actually they were formed exactly at the same moment, at the early stages, like a binary system. When we talk about stars and planets, I've explained to you that actually binary systems are not very rare. So maybe they have been formed exactly at the same time. Okay? So if it's the case, then they should be exactly the same. Same chemistry and same structural properties. Same geologic activity. So the moon should have a core, a magma should be exactly like a small replica of the Earth. So that's one possible scenario. Maybe the moon was captured by the Earth. So like I said, for Mars, let's say that the moon was just wandering around and get too close to the Earth and get trapped in a Earth gravitational field. However, there are big bodies. So the Sun, the Earth, and the Moon are very big. The Moon, once again, is quite a big body compared to the Earth. So this is what we call a free body interaction. That means that you have exact configuration to have the Moon trapped in the Earth gravity field, but not by the Sun gravitational field. And if you do a bit of gravitational studies on that, this three-body problem is very, very rare. So it's very improbable that it will happen. Could have, but it will be very improbable. And also something I didn't mention here is then there's no reason why you will have similar chemistry between Earth and the Moon. They may be totally different, if it's the case. Then there is another scenario. Imagine that actually before Moon and Earth were only one big ball, but the rotation of the ball be very fast and the piece get detached and form the Moon. So this is one possible scenario. The problem is for it to happen, you need to have very, very strong rotation of the initial body, and probably will have totally destroy the body itself. So this kind of scenario are very unlikely too. If this was the origin, probably the Earth would have been destroyed as well in the process. So we don't think this. And the last one is actually the Moon was formed in a giant impact of the Earth with another large body. Imagine that there is, at the early stages of the formation of solar system, you have a very big planetesimal, let's say a small planet that is wandering around and collides directly with Earth. And it's a very, very energetic phenomenon. And then after a while, the system relaxes and you end up with the Moon and the Earth turning around together. And actually, this is the best explanation so far. And I will demonstrate you why. So just by what I told you in a minute, those two are very improbable. So very rapidly, we narrow down to or they were formed together, or the Moon was formed by an impact between Earth and another body. Something like that. So let's start with facts. This is the Moon and the Earth. So once again, the Moon is only 1/4 in terms of diameter of radius than the Earth. The axis of rotation of the Earth is 23.5 degrees compared to the ecliptic, while the rotation of the Moon is almost nothing, 7 degrees. So there's no season on the Moon. Surface temperature of the Earth is between minus 73 to 48 degrees Celsius. And on the Moon, it's always negative. There's no atmosphere to trap, so no greenhouse effect. So it's always cold on the Moon. Earth has a thick atmosphere with a mild greenhouse effect, while the Moon has no atmosphere. There are lots of liquid water at the surface of Earth. You all know that. There are actually no liquid water on the surface of the Moon, but there is ice in the poles visible. So and in the shadow. So there are some water on the Moon, but not on liquid form. So due to the presence of the atmosphere, Earth has an active wind and water erosion phenomena, while of course Moon has no atmosphere, nothing happened. There are traces of impacts in both Moon and Earth. And there are active volcanoes on Earth, but there's no more any active volcano on the Moon. You have earthquakes, we know that here. Actually, there are some moonquakes that have been measured. So the Moon has seismic activity. Earth has a very strong magnetic field, Moon doesn't have. On Earth, there are a few craters, while actually on the Moon there are many, many, many of them. And there is a plate tectonics on Earth, when none on the Moon. So the Moon is actually geologically active. The Earth is actually geologically active, while the Moon is not. That's the main difference. It has been in the past, but it's not anymore. So as there are small moonquakes, we can do geology. So we can study the actually structure of the Moon. And what is pretty obvious is actually the Moon has no liquid mantle anymore. It's all silicate and it's all solid. We may have evidences of a core, but still under debate. But for sure, the Moon has a crust and a mantle, but the mantle is not solid anymore. It's solid, it's not liquid anymore. So there's not enough heat produced by the core of the Moon to liquidify the mantle like it happens on Earth. So even if there is a core, it's probably very small, and the radioactivity is probably very minor, and it's not melting down the mantle at all. Some of the facts about the Moon, I mentioned that at the start. If you do a mass ratio of the Moon compared to the size ratio, you realize that the density of the Moon that means the mass divided by the volume, is far lighter than the density of Earth. There are less iron on the moon than on Earth, but more aluminium and titanium. Actually, the moon's chemical signature is extremely similar, worryingly similar, to the Earth mantle chemistry. So if you remember from the fourth scenario I mentioned at the start, the scenario of a body captured, so the moon being a body captured by the Earth, is probably ruled out by this. There's no reason why the chemistry of the moon would be exactly the same as the chemistry of Earth if it was just captured. The moon does not orbit in equatorial plane of Earth, or ecliptic actually. I mentioned that because when we are talking about eclipse, the moon orbits around the Earth, is not in ecliptic. And the Earth-Moon is having a very high angular momentum, mentioned with the Tidal Effect, so there is a very, very strong coupling between those two. So, this tells us that probably Earth and Moon has something in common, because the chemical signature of the Moon is very close to the chemical signature of the mantle of Earth, but the structure of the Moon is very different from the structure of Earth. I mentioned that. And the fact that there is barely any iron on the Moon tells us that actually Moon and Earth are not probably formed at the same time. So it's ruling out the scenario where Moon and Earth were formed at the same time. Because if they were formed at the same time, the composition overall should be exactly the same. There's no reason why there would be more iron in the Moon than more iron on Earth. So the best scenario is impact between two protoplanets, early stages of the formation of our solar system. So something that happened 4.5 billion years ago, you had a protoplanet the size of Mars that impacted the protoplanet of the size of the Earth. And it's a very, very strong phenomena, but it explains a lot of things. It explains the chemistry. I will show you the simulation in a minute. Explain why Moon and Earth are so much in common, but being somehow different. It explains the orbit. It explains also why the axis of the Earth is slightly tilted compared to the ecliptic plane. So when we talk about scenario of formation of the solar system, I will show you that main part of the planets in our solar system have the ecliptic plane almost perpendicular, the rotation axis almost perpendicular to the ecliptic plane, while the Earth is tilted. But if there were at some point an impact on Earth, it may be responsible of this change of axis of rotation. And the fact that Moon and Earth are so much coupled in terms of very high angular momentum, that means that actually the Moon is turning very fast around the Earth, far more faster than it should be. Then it's also in favor of this kind of scenario. So I'll show you this simulation from people from the University of California. So this is an interaction between two bodies. The red part is the heaviest part, so mainly composed by iron, that is the core of Earth. And the yellow part is the mantle part, that is a bit lighter. So you know that when we talk about the structure of Earth, we have an iron core, so a very highly metallic core, and a mantle that is a bit lighter. Okay, so here you divide the two bodies that were formed initially in the solar system, so they are very similar, just different size, but they both have a very heavy core and a lighter mantle around it. And then you make them interacting. And this is what happens. So you have interaction, so it's obviously very destructive. And so during this phenomena, what you see is that there is part of the initial body that has been ejected. Okay, so the yellow particles are the mantle particles. They are spread all around the place, but very rapidly the iron core is sinking back at the center of the system. So let's play it again. So here you have the impact. Okay, so both systems are extremely distorted, almost totally destroyed. And here Okay, so follow here. Somewhere around here, you will see a planetesimal, a yellow blob formed. So if you this here, okay. So what happened is that if you have a system where the second body that is formed around there, you have seen the yellow blob is formed mainly from the mantle, while all the heavy elements are back to the center of the system, to the core of Earth. So this is a very, very good way to explain those different parts I mentioned here. Same chemistry, different orbits, explain the difference of orbits of the Moon Earth system, and very high angular momentum. With that scenario, you explain very well why there is no iron on the Moon, but while the signature, chemical signature of the Moon is very close to the chemical signature of the mantle of the Earth. Okay. Do you have any questions? Okay. Okay, thank you very much.